The setup we have here is back to using the signal generator, but this time the output goes to two places. It goes to the top red trace on the oscilloscope screen, and it also goes to the input of this instrument here, which is the filter. The output from the filter is also shown on the oscilloscope screen at the bottom in yellow. In the simplest terms, a filter is a selective component which allows some parts of a signal to pass, but doesn't allow other parts of the signal to pass. The way I have it set up at the moment is what we would describe as a low-pass filter, and it's called that because it lets low-frequency components pass, but doesn't let high-frequency components pass. So at the moment you can see from the oscilloscope screen that the input and the output look pretty much the same. We're in what we would describe as the pass band of the filter because it's allowing this signal to pass through. If now I increase the frequency of the signal, the output gets smaller and smaller. We're now moving into the stop band of the filter because at higher frequencies the filter won't allow those components of the signal to pass. If I increase the frequency again and bring the filtering effect into play, you'll notice that the output gets smaller and smaller as the filter begins to filter out those higher frequencies, but the output always retains the same shape. It always looks like a sine wave. This is one of the fundamental properties of sine waves. When they go through a filter, they might be delayed, what we would call a phase change. They might be filtered or attenuated, they might become smaller, but they always retain their shape. Now I'm going to repeat the experiment, but switch the input from a sine wave to a square wave. Immediately you'll notice that the shape of the output has been changed. So this is a low-pass filter, and as you might have imagined, some of the sharp edges, which of course are the fast-changing bits of the waveform, have been smoothed over a little bit. Now I'm going to just increase the frequency of the square wave input and watch what happens to the output. Not only does the output signal get smaller, but in addition it changes its shape, so now it looks much more like the sine wave. You can take away from this experiment that even simple filters can change signals in ways that are difficult to predict. And so it seems likely that if we're going to introduce filters into our physiological measurements, then we need to understand how they're going to affect the measurements, or else we could end up in a bit of a mess. Keep in your mind how the low-pass filter rejects the sharp, fast-changing parts of the square wave, and you're just left with an overall sense of the underlying waveform, what we would call the fundamental frequency, in fact. Next, I'm going to swap from a low-pass filter to a high-pass filter with exactly the same input signal. So now I'm going to reduce the frequency and see what the effect of the filter is. We've retained those sharp edges, the fast-changing, high-frequency parts of the signal, but the slow-changing parts, the tops and the bottoms, where the signal isn't changing at all, are distorted. To summarise, we have low-pass filters that keep the slow-changing parts of a signal and reject the fast-changing elements. And we have high-pass filters that do exactly the opposite. They retain the fast-changing elements of a signal and reject the slow changing parts. In our ECG, for example, we have a relatively slowly changing signal, and so a low pass filter would help to reject some of the high frequency noise that is causing the interference. In the final experiment, I'm going to introduce a high pass filter. First of all, notice how it's going to remove the slow changing ECG signal and leave behind what previously we thought was noise. Except that isn't noise at all. I'm going to clench the muscles in my arms. You're seeing and listening to the EMG, which is the electrical activity from the muscles in my arms. The demonstration makes two important points. First of all, that noise is simply an unwanted signal. So what's noise for one person might be signal for another. It all depends on the context. And second, that we can use high and low pass filters selectively to tune into the components of the signal while we exclude the frequency components of other signal sources that we may consider to be noise. In the subsequent lecture on digital signal processing, you'll get a little bit of a better insight into some of the signals that we're recording and actually how some of this instrumentation works. And you also see ways to analyse your data in a manner that simply wouldn't be possible with instrumentation like this. Till next time.